Hi everyone, so today's webinar is going to be on practical skills. So some of the practical work that we're doing in biology this semester is we're looking at how to design an experiment, the practical skills required, how to present the data that we collect, and how to also interpret and evaluate that data. So when you design an investigation, you need to identify what needs to be observed, the measurements that need to be taken, the techniques that you need to be using to collect the data, and the apparatus or the measuring instruments that will be needed to measure that data. So the variables that we need to identify, firstly we need to identify the independent, dependent, and controlled variables. So the independent variable is sometimes referred to as the experimental variable, and it's a variable that is deliberately changed. And this variable should always be on the x-axis. So if we're looking at photosynthesis in plants, for example, and we're changing the light intensity, then the light intensity in this case would be the independent variable, because we are changing the light intensity to see how that impacts on a plant's ability to photosynthesize. So the dependent variable is the variable that may change as a result of the independent variable, and it's plotted on the y-axis of the graph. So if we're talking about our photosynthesis prac, looking at how light intensity impacts on growth, the rate of plant growth is the dependent variable, as that's the variable that is changed as a result of changing the light intensity. And all other variables are what we refer to as controlled variables. So these are the variables that need to be kept the same during the experiment, because we need to make sure that we only have one independent variable to ensure that the variable that is impacting on the results is the independent variable and not another variable that we haven't remained the same. So for example, we're looking at our photosynthesis practical, we need to ensure that the temperature, the amount and source of water, the type and amount of fertilizer used, the soil, the type of containers, the type of plant, they're all the other variables that we need to make sure are the same so that the only variable that we're changing is the independent variable. So whenever you conduct an experiment, there is usually an aim, and that is the purpose of the experiment. So why are we even doing this? Why are we even investigating this hypothesis or question? So the aim needs to include both the independent and dependent variable, and usually starts off with to investigate or find out. So for the example of plants and photosynthesis, our aim would be to investigate the effect of light intensity on plant growth. And that is the aim of the experiment. So when we conduct an experiment, we have what is called a hypothesis, and this is what the experiment is designed to test. So we call that a testable statement, and that statement usually connects the independent and dependent variable and is written as what I would call an if-then statement. So in the example of photosynthesis and light intensity, we would say if the light intensity is increased, then the rate of growth of plants will increase. So it's an if-then statement, and you need to be specific as well. Now, in all practical investigation, you are going to have errors. It's unavoidable, and it's important that you are able to identify the errors. And the main two types of errors that we see in an investigation is random errors and systematic errors. So random errors are caused by a factor that randomly affects the measurement of a variable. And the key word here is random, because not all measurements will be affected by this error, and that's what makes it a random error. So what happens is when you graph your results, you'll see what's called scatter, where you've got data that's a little bit all over the place, and that's the result of random errors where there is a variation from what we should be seeing because of that error. So random errors are usually linked to how good you are at measuring using an instrument or the resolution of a measuring instrument. So if you're using a centimeter ruler to measure really small things and it doesn't have millimeter increments on there, then it's likely that you're probably going to have some random errors because the resolution in this case is not high enough to measure that uh, the results correctly. So if we have a look here, we can see the difference between high and low resolution, which is the same as like pixels in a picture. The better the resolution, the less likely it is that you'll have random errors. So examples of random errors include the inconsistent reading of scales. So if you didn't zero your scales properly, you may end up with an error. If you don't measure volumes in a measuring cylinder correctly, so that's what's called, if you don't have the meniscus properly, you can have parallax error, which is where you're not viewing the level of liquid in the volume, the cylinder properly, and you're not actually recording it correctly. Or another type of random error might be if you're using a timer, if you don't reset it properly, or the time it takes for you to start the timer after the experiment has started, the reaction time, that is also a random error as well. So the way that we reduce random errors is by repeating the experiment again, improving the technique, so suggesting at ways that we can improve it to reduce the effect of random errors. Now, when we look at our data, if we draw a line of best fit, often that will help to reduce some of the scatter that we see, and that could reduce the effect of random errors. And also increasing the number of samples, so having a large sample size and then averaging all of the samples into an average will also decrease the effect of random errors. It is really important to understand that random errors can never be eliminated. We can reduce them, but there's always going to be a certain amount of human error, no matter how good you are as during the practical. There will always be some degree of random error. So the other type of error is a systematic error, and this is where the error affects all the way through the experiment, and it's a constant difference or error that affects all the results the same and is often different from what we call the true value. So values that we obtain that will have a systematic error will either be consistently high or consistently low. And it's usually the result of not calibrating the measuring equipment that you're using correctly. So if you can, before you start an experiment, checking the calibration of an instrument might help to eliminate a systematic error before you even start an experiment. So for example, a set of scales that don't work properly, that aren't calibrated correctly, are going to result in a systematic error that incorrectly measures the weight. So if we have a look at an example of a systematic error, we might see that for a balance or a scale, for example, all the readings might be calibrated by 0.05 of a gram lower for all results. So it's systematic. It is all of the results are affected by this error, unlike random errors where only some of the results are affected. So examples of systematic errors include a thermometer, glassware that might have imperfections on it, so there might be it may not correctly represent the volume that it says it is, and chemicals that may have reacted over time or become contaminated may not be a true representation of the interaction then occurring. So systematic errors cannot be eliminated or reduced by repetition, and you cannot average your results to reduce systematic errors because it is not random. It is a movement off the true value. So the way that you eliminate systematic errors is by upgrading or changing the equipment, or recalibrating the instrument, or using a higher grade material to eliminate those errors. So you can potentially eliminate a systematic error, whereas random errors, as we know, can never be eliminated but just reduced. So we can determine whether there is a systematic error present by repeating the experiment and using alternative equipment or fresh sources of chemical. So if we're looking at using gasoline in an experiment, for example, if you have a look at new gasoline compared to aged gasoline, it's going to have a different effect whenever we collect our results, because it's this aged gasoline, obviously something has happened here that's changed the way that it interacts with the environment around it, and it's not going to give us a true representation of how gasoline works properly. So the other thing, when I talked before about random errors and sample size refers to the number of samples in an experimental group. If you increase the number of samples, this allows for an average to be calculated, and this can minimize the effect of random errors. So the larger the sample size is, the smaller the effect of random errors in your data, and the more precise your experiment will be in terms of collecting results. So in terms of repeating the experiment, you repeat experiments to hopefully identify systematic errors, but it's also a way to verify your results, because all scientific investigations need to be able to be repeated to have the same results again and again and again, because that is an indicator of a well-designed experiment. So there are a few other technical terms that you need to be familiar with. So the first is precision, or what we call reliability. And that's with around how easy is it to reproduce the measurements that we collect from an experiment again on a different day with different equipment. And this relates to the scatter of measurements. And therefore, if we're talking about scatter, we're talking about random error. So if we see low scatter, that means that we have higher reliability or precision. And if we see high scatter, then we see lower reliability. So having a look here, we've got two graphs, and we have put a line of best fit through the data to try to reduce the effect of random errors. Now you can see that if we have a look at graph A compared to graph B has a tighter fit in that the scatter around the line of best fit is minimal in comparison to graph B. So therefore, graph A. So graph A has lower precision because of the higher amount of scatter around the line of best fit, meaning that graph B has higher precision. So accuracy is the other measurement that we need to take into consideration. So accuracy relates to how close are the measurements to the true value or agreed value in an experiment. So the results that you produce, how close are they to what you expect to see? And accuracy is affected by the skill level of the individual in collecting and recording measurements from a specific instrument. So systematic errors need to be detected if the result is to be accurate, because we know systematic errors are either above or below the true value, which is what accuracy is all about. And the way that we again determine systematic errors is by repeating the experiment. So if we have a look here, this student A 1 and 2 and have looked at the boiling point of water. Now we know boiling water boils at 100 degrees Celsius. So if we have a look at student 1, we can see that their results are all over the place. They have a range of 6.9 degrees Celsius, which is huge in comparison to, say, student 2, which has a range of 0.2. So students 2, their data is more reliable because they have less scatter. Range here indicates scatter. So student 1 has high scatter, low reliability. Student 2 has low scatter and therefore high reliability. If we have a look over at student 3 and 4 here, we can see that student 2 has, although they have they have very precise data, reliable data, they're actually off. They have a systematic error because we know that water boils at 100 degrees Celsius, but according to students 2 data, it is boiling at 102. So there must be a systematic error there, and therefore they have low accuracy. Student 3, however, has an average of 100 degrees Celsius. So therefore they have high accuracy because their data is as close to the true value of boiling water. So this just is a diagram to show the difference between systematic and random errors and looking at precision and accuracy or reliability. And we'll just keep on skipping through these. So when you, after you've collected your data, you then need to include a table of results. So the independent variable always is placed in the first column, and the dependent variable is placed in the next column over. Units must be included in the heading of the column of data, and they must be included in brackets. So here we've got table results. The experiment was looking at the hair color of some of the teachers at open access. So we've got the teacher's name, so Juan, Mark, and Kelly, and then we've got the hair color, which is black, brown, and blonde. So here, this is the independent variable. So that is always placed in the first column. And then we have the dependent variable that is placed in the next column over. Now, looking at this, we have included the heading, which is very important in a table of results. We've included the actual results, and that's what you need to include in a table of results. So if we were to go on to graph those tables of results, this is a table of results here, and then based on the type of data we have, we can then graph it. So we've decided to use a column graph to represent the data here, and you can see we've got hair color along the x-axis because it's the independent variable, and number of people is along the y-axis. We also have a title on our graph as well. And again, here we've got another type of data. We've got what we call, and we're going to use a column graph. And now this title here is not really inappropriate. Is this like a preference for food, or what were we actually trying to measure here in type of food type? Is this a preference? Do 4 people like pizza? So really our title should be the favorite food as measured by different people. Now if we've got different data like this, we've got time on as the independent variable and then temperature, then we need to graph something as a line graph, which we've done here. So when we draw graphs, the independent variable is on the x-axis and the independent variable is on the y-axis. We need to include an appropriate scale so that our data fits nicely on the graph, and we need to include units as well. So units are included in brackets after the name of the independent and dependent variable, and usually include a measurement, so it might be meters, for example. And then we also need to include a line of best fit, which gives an average trend of the data. And we need to include a title as well. So when using a correct title, when describing our results, we can't just say independent variable versus dependent variable because that's not descriptive enough. So if we're looking at the effect of light intensity on growth rates, the title should clearly connect the independent and dependent variables in a detailed way. So rather than saying light intensity versus growth rate, we would say the effect of varying light intensity on the growth rate of plants. So the key here is to be detailed. So whenever you plot your data as points, you need to include a line of best fit that represents a trend. So a line of best fit is basically an average representing the trend of data. Now, when you include a line of best fit, you will notice that some lines of best fit will fit the data better than others. So we can see here in this top graph that we have a lower degree of random errors compared to the bottom graph because we see higher scatter in the bottom graph compared to the top graph. Now, after you've graphed all your results and you've put in some tables and graphs, you then need to actually start analyzing and evaluating the data. So the first thing you'll do is you'll describe the results. So looking at specifically the numerical values, if you were to tell someone about your results, you would describe that to them without having to show them any graphs or any of your results. So you would tell them about the numerical data that you collected, you would tell them about the trend of data. Do we see an increase with an increase in time? Then after you've described the results, you need to explain why we see the pattern of results that we do. Once you've done that, you then need to identify random and systematic errors, and you need to comment on the reliability and accuracy of your experimental data. Is it reliable? What's the scatter like on the graphs? What's the accuracy? Do we know, if you're looking at the boiling point of water, is your data accurate in terms of what we know about the boiling point of water? All random and systematic errors that you address, you should include a suggestion for and about how we can improve to hopefully reduce or eliminate the random and systematic errors. The last thing that you need to include is a conclusion. So you need to talk about a summary of the experiment, what it is that you found, and whether your hypothesis was either supported or refuted. Experiments never prove a hypothesis, they only ever support or refute.